2022 marks the 150th anniversary of the birth of Paul Langevin, the French physicist who created the enabling technology for ultrasonics. Our title comes from the 1946 book on piezoelectricity by the American physicist Walter Cady, where he describes Langevin as the originator of the science and art of ultrasonics. Today, I hope to demonstrate why this is so. Paul Langevin was born in a small apartment in the Montmartre district of Paris on the 23rd of January 1872 into a family of modest means. Number 8 is the second house down on the left-hand side of Rue Ravignan. The ground floor now houses a small bar called Chez Camille. When I visited Paris this summer, I could see no plaque to mark this house as Langevin's birthplace. In 1948, 2 years after his death, his ashes were laid to rest in the place of honour for only a few of France's greatest men and women, the crypt in the Pantheon. His lifetime friend and companion, the double Nobel laureate Jean Perrin, was honoured with him in the same ceremony. In 1995, the same honour was finally given to Pierre and Marie Curie. Langevin was a precociously outstanding student. His association with the School of Physics and Chemistry, known as ESPCI, lasted from his student days to the end of his life, by which time he was its director. He was also appointed as professor at the Collège de France. It was here that his lectures and courses created his reputation as an outstanding teacher, able to explain clearly the deep challenges that were shaking the foundations of classical physics at that time: quantum theory, radioactivity, relativity, and so on. By the end of his life, he'd received 6 honorary degrees, was a member of the Royal Society of London, the Soviet Academy of Sciences, and of 6 scientific societies in other nations. In France, he was awarded the Grand Croix of the Légion d'honneur. His early brilliance was recognised by the award of an overseas scholarship from the city of Paris, and he spent a year in J.J. Thomson's Cavendish Laboratory in Cambridge. Here, he worked on gas ionisation, the topic that he then developed for his doctoral thesis. Many colleagues felt that it was this year that changed his life. Thomson's team of young researchers included 2 of particular significance. The New Zealander Ernest Rutherford was there. Later, when he was physics professor in Manchester, England, he played an important part in the early story of ultrasonics. And John Seely Townsend was the first to formally promote Langevin internationally by proposing him for the 1910 Nobel Prize in Physics. This was the first of 15 nominations by scientists from 8 different nations, the last in the year of his death, 1946. They were all unsuccessful. In retrospect, his scientific contributions, quite apart from those in ultrasonics, should have resulted in him receiving a Nobel Prize. Langevin had a thorough grasp of the changing landscape in physics and could express it mathematically. His simultaneous development of Einstein's famous equation, using different and more general principles, led Einstein to observe later that it might be called the Einstein-Langevin equation. The missing factor X in his statistical analysis of Brownian motion appears in modern statistical analyses as widely varied as rainfall prediction and the movement of the stock market. His mathematical formulation of diamagnetism has retained validity in spite of later deeper understanding of the atomic basis of magnetic behaviour. These clippings are all from his collected works brought together after his death by his eldest son, Jean. By the first Solvay Physics Congress held in Brussels in October 1911, he was part of the top flight of European physicists. Language was no barrier for him. He was fluent in both English and German. But there's a non-scientific subtext to this photograph. Jean Perrin is keeping close to Marie Curie, while Einstein keeps an eye on Langevin. In November, the fat hit the fan when Langevin's wife, Jeanne, released copies of Marie Curie's letters, including one setting out how Langevin could leave his wife. Their marriage survived, but it was never the same. Langevin attended all the subsequent Solvay conferences until his death, and he was the chairman for the 6th and 7th in 1930 and 1933. Here is a chart showing Langevin's published scientific output. I've excluded his publications on non-scientific topics, such as education and politics. The graph is broadly bimodal. The period before the First World War up to 1914, characterized by contributions in the areas already noted: ionization, magnetism, kinetic theory, and relativity. The period after the war shows a different distribution, dominated by publications in ultrasonics, together with several tutorials on the theory of relativity. I'll show a detailed breakdown of his ultrasonics publications later. Langevin was an anti-war activist. When war broke out in August 1914, he joined the Territorial Reserve, at the same time continuing his teaching at ESPCI. Other friends went in different directions. Jean Perrin became an officer in the Engineering Corps. Marie Curie devoted her time to military radiography. In January 1915, Marie Curie travelled with Perrin in their mobile radiography units to the front line, from where they wrote a joint letter to Langevin. In it, they pressed him to apply his abilities to the war effort. And at about the same time, a document arrived on his desk, written by a Russian revolutionary exile then living in Switzerland, Konstantin Chalowsky, describing an ultrasonic method for detecting submarines, which he'd been working on since 1912. Langevin bit the bullet. This slide outlines the steps toward Langevin's submarine detection system. The suggestion for using a directed beam of ultrasound for underwater detection using echoes had been proposed by the English physicist Lewis Fry Richardson after the Titanic disaster, but no system was ever built. The principle was right, but the method was impractical. So what transducer could emit a sufficiently high-intensity sound beam? And what detection system would be sensitive enough and sufficiently noise-free to act as a receiver? Richardson's whistle, Chalowsky's electromagnetic diaphragm were rejected as sources of ultrasound. For a year, Chalowsky worked with Langevin and succeeded in demonstrating that a mica singing condenser emitted an ultrasound beam that could be detected using a small carbon granule unit at the focus of an acoustic mirror. The system operated at about 100 kilohertz. This was the basis of the first patent, filed just about the same time that Chalowsky left Langevin's lab. Then, as we will see, Langevin realized that a plate of X-cut quartz could operate as a receiver to replace the carbon granule microphone, and this soon led to his demonstration of ultrasound generation using quartz, so opening the possibility of a simple pulse echo system using the same transducer for transmission and for reception. The work transferred from Langevin's Paris laboratory with its tiny sink to the naval dockyard in Toulon. Langevin assembled a team of engineers. Chalowsky left, replaced by Marcel Tournier. Lieutenant Colin brought naval electronics expertise and equipment.